Hello everybody. In this video, I'm going to show you how we can use our um, data analyst or our hypothesis dashboard. And what we're going to do is we're going to move from linear regression to multiple regression. So in linear regression, we took a single x variable and we used it to predict a single y variable. Now what we're going to have is we're going to have a whole bunch of predicting variables. In this example, we're going to have 4 that are going to be used to predict a single thing. So let's look at it. So it says a regional housing analytics firm wants to understand what factors most influence the cost of apartment rentals. They collect data from 38 different rental listings, record each apartment square footage and distance to the city center, and they do also the number of bedrooms, the age of the building in years. Their goal is to build a multiple regression model to predict monthly rent based on these 4 housing characteristics. This model will help renters, landlords, and city planners better understand how various features contribute to pricing. The firm utilizes a significance level of 5% to determine which predictors are statistically important. So we're going to click on our view data. Let's go ahead and copy it. And let's go ahead and paste. All right, so we've got our data all pasted in. And if you look over here, we have our significance level of 5%. Okay, so here we've got our 4 predicting variables and we have our monthly rent for our data here. Okay, so the type of data being analyzed is still just numerical by numerical. And we say how many predicting variables are being investigated. So we have 4 predicting variables that are being used. So the response or the dependent variable in this is the monthly rent in dollars. The population that we're using is going to be all the rental apartments in the region, and what we're going to be using is this like multiple linear regression. Okay, which assumptions must be checked? So we need to check like linearity, independence, normality, and constant variance, just like we did in linear regression. And then we want to ask, okay, what is the equation for our regression line? Okay, so how we find that, just like we did before, we go to our coefficient column over here in our output. So we go to our coefficients. This is our intercept. This is the coefficient times the square footage. This is the coefficient times the distance to the city center. This is the coefficient to the number of bedrooms. This is the coefficient to the age of the building in years. And so if we see it, that's how we build up our equation. So now we have this interesting question that says how many predictors in this model are statistically significant. We also might want to see, is the model overall significant? So we still look at our F statistic and we compare it to the p-value, and we look at our p-value. So our F statistic is our test statistic. P-value is it significant? So here we have a very small p-value, so yes, it is significant. And then we can come over here and we can look at which of these predictors are significant. And here we only have 2 that are significant. Notice how we have 2 p-values for the individual predictors that are significant. Looks like square footage and the age of the building were not significant in this particular model. So now it says, what is the predicted rent for an apartment with these values? Let me just do this calculation for you real quick to show you how we would do this. We would do equals the slope, and we're going to include all of the predictors, even if they are insignificant, because you don't know how to take care of them right now. So we're going to do the slope of the square footage times the square footage over here, which in this one is 861. And we're going to do plus distance to the city center times, it's going to be 4 miles, so we'll do 4, plus number of bedrooms times 4. And we'll do plus the age of the building times 49. And if we go hit enter, we get this 1537. And that's our correct answer. Nested asks for the test statistic, F43. Asks for the p-value, which in this case is essentially 0. Interpret the slope for the square footage. So here's our slope. And it says that each square foot increases the rent by about 0.07. 0.07. So it's like, yes, it's increasing, but it's increasing in negative. Little funny way to say it, but that is correct. We need to interpret the r squared. It's the same thing that we interpreted before. So here we interpret the r squared up here, where we can say that roughly 84% or the 0.8398 of the variation in rent is explained by the overall model. Now it asks for the confidence interval for the slope of the square footage. So if we look at square footage and we go look at the slope, or the confidence interval of its slope, it's going to be from negative 0.2574 to 0.1161. So there it is in a nutshell of like how we quickly do it. The only thing that's kind of different is now instead of just having one output here in our intercepts and our slopes, we have multiples. In this case, we had four. We know which ones of these individual predictors are significant by looking at the p-value, and we know the slopes for the prediction models right here, so we can build it all together. So when we're building it all together, it's just like that. Now, if you go look at your flow chart real quick, let me pull that up for our regression analysis. It also goes through and shows you how you do your model building. And this is handling for both linear and multiple regression. If we're doing multiple regression, your null and alternative hypothesis is that all of the slopes are zero, and or the beta 1, beta 2, betas for each of the slopes are zero, and the alternative hypothesis is at least one of the slopes is significant. Notice how those are written out there. Let's go down and see, okay, so how you build these. You plug in your values, you build up your equation just like we worked on, and we build those from the coefficients. It's just instead of linear regression was just this first one, and then multiple linear regression is just we add on extra ones for every additional predictor that we have. But you still interpret like the p-value and the r-squared all the same as before. And I think that that's about it. So that's a little crash course on how you do multiple regression.